let's listen up for a second. Nothing too new today chemically. We're looking at precipitation reactions, the kind of stuff that we've already looked at several times. Just a real quick reminder, this is kind of the physical scenario that we're looking at. In a precipitation reaction, we've kind of got the ability to either be in the solid state, and these are for these ionic solids. So they can be in the solid state where the ions are stuck together by their kind of electrostatic interactions, their electronic forces, or they can dissolve in solution. When they dissolve in solution, they end up making those electric interactions with the water molecules. So the interactions in the solid favor the solid, the interactions with water favor the dissolved state. And then the other thing that we have is entropy that kind of guides these. In general, there's an entropic push to have the aqueous state because the matter is spread out over a larger volume in the aqueous state. And the enthalpy of the reaction will largely have to do with the relative strengths of the electronic interactions in the solid and the liquid. If the solid interactions are more favorable, then but the thing is still insoluble, it's still dissolved, or sorry, it's still soluble in solution. If these interactions are stronger than these, then when it goes to the dissolved state, it'll be endothermic, it'll absorb energy. If these interactions are stronger than these, then when it goes in the dissolved state, it'll release energy, it'll be exothermic. We saw that a couple weeks ago when we were dissolving salts and we monitored the temperature change of the solution. Okay, so we're just playing around with these reactions. Something that I said a couple weeks ago that I wanted to reiterate, and this table here makes it really easy to talk about it, was that there's kind of characteristics that ions have in terms of whether or not they're soluble or insoluble. And it turns out that the multiply charged ions, so if you got like a phosphate, PO4 3- or ion or something like that, or like a cation that has a 2+ charge, we've got a lead cation, it tends to be that those multiply charged ions are better at forming those favorable interactions in the solid state. And so they'll substances of multiply charged ions will tend to be less soluble. And you can see that just by glancing at this table. This table takes pairs of ions and tells you whether or not they're going to be soluble or insoluble when paired together. And if you look at this last column here, the phosphate ion, PO4 3-, it's a 3- charge on that guy. When paired with everything from silver down, it makes a solid. So the phosphate ion is insoluble with everything except for these guys here at the top, the H+, the Na+, and the potassium, the K+. Well, that's because the phosphate has got 3 negative charges, and so it's really good at making those electric interactions in the solid state. Carbonate, kind of the same way. This guy is insoluble with the better part of the cations that are available in this table. It's only soluble with just a handful of them. But then you get back in here to these singly charged ions, and you'll note that a lot of these singly charged ions are soluble with many of the
you don't like them on their face, like when they like turn the camera on.
So again, the singly charged stuff, not so good at forming the solid. The doubly and triply charged stuff, better at forming the solid because of those interactions. It's not always perfectly safe to associate charge with solubility, but most of the time it is. So here's what we're doing today. Today, we're just kind of taking advantage of the solubilities of some of these substances to look at how we can pull them out of a body of contaminated water. We're taking solutions of lead ion and copper ion. Why do we care about methods for removing lead and copper from water? Anybody been listening to the news lately? Flint, Michigan, we've got lead pipes, right? If the chemical conditions in those pipes aren't maintained at certain levels, high pH. If you don't keep the pH of those pipes right, these ions leach out when their electrons are removed. So we've got a problem with this. we've got pipes that are made of lead, we've got pipes that are made of copper, and so all of our bodies of water have problems with copper and lead contamination. Today we're going to be using the solubilities of lead and copper to remove them from solution. We'll take solutions of lead nitrate and copper nitrate. Can you by looking at this table, can you tell me what state the copper nitrate and the lead nitrate are in initially? Is this NO3 minus ion, one negative charge? If you look down the column, it's soluble, with almost all of the cations. Well, with all of the cations. So that NO3 minus, the single negative charge, is not very good at making those interactions in the solid state. So most cations, when paired with it, dissolve into solution. So we've got aqueous solutions of copper and lead, and we're going to add to them a component that will preferentially precipitate out our positive ion. Now, for the lead solution, we're going to use potassium iodide, Ki. And if you notice here on this table, your Pb2 plus and your I minus are listed as forming a solid when paired together. And so those are insoluble together. So we'll take a solution of lead nitrate, we'll dump in some potassium iodide, and an insoluble lead iodide precipitate is going to form. All right, we'll then gravity filter that precipitate out, we'll remove it, weigh it, and determine whether or not we're able to pull all of it out of solution. Your copper ion happens to be insoluble with phosphate, and so we're going to be taking a phosphate salt and putting it into our copper nitrate solution, and we're going to precipitate out that copper phosphate. The only thing that's really new about today's reactions are that you're going to have to do some math to predict how much of the other substances are required to interact. Here's how that math works. A little bit about how that math works. So the first thing that we're going to do is we're going to start with the balanced chemical equation. Now we've got a lead nitrate solution. We're going to add Ki to it. It's going to form a lead iodide solid and a potassium nitrate salt solution. Does that equation make sense to you? Is there anything wrong with that equation? What's that?
It's not balanced.
It's not balanced. It doesn't obey conservation of mass. We've got different numbers of ions on one side and the other. And so the first thing we're going to do is to choose the appropriate coefficients, such as to balance the chemical equation. Lead forms the 2 plus ion. How many I minuses are going to be required to neutralize one Pb2 plus? Remember, when we make these ionic solids, there has to be charge neutrality. That means for every positive charge, we have to have one negative charge. So if we've got a Pb2 plus ion and we're pairing it with I minus, we're going to need 2 I minuses for every Pb2 plus, right? And so we could put a coefficient of 2 in front of that Ki, because that'll provide us, if we have 2 moles of Ki for every 1 mole of PbNO3, then we'll have 2 I minuses for every 1 Pb2 plus. So we'll end up forming 1 mole of PbI2, and we'll have left over 2 moles of that potassium nitrate, soluble potassium nitrate salt left in solution. So first thing you do, look at that equation, make sure that it's balanced. You're going to be asked to take a solution. We've got a stock solution that is 0.02 grams per milliliter of lead nitrate. You're going to take about 10 milliliters of that solution. You get to choose your own volume, but 10 milliliters was a rough approximation. And based on the volume of the solution that you're using, you'll predict how much of the other components are necessary for the reaction. And the way that works is this. The first thing you're going to do is going to ask yourself, in that volume that I've selected of the lead nitrate, how many moles of lead nitrate are present? So you've got 10 milliliters, first step of this calculation, you've got 10 milliliters of a solution that is 0.02 grams per milliliter. Multiply those together, milliliters cancel in the numerator and denominator, and we find out that we have exactly 0.2 grams of lead nitrate. So now we know the mass of the lead nitrate in that solution. We've got to turn that into a number of moles. the balanced equation always relates moles of one thing to moles of another, and so if we have a number in mass, we've got to convert it right away to moles so that we can relate it to other components. For that, we'll need the molar mass of the lead nitrate. There's this X is a variable. You guys can calculate it. This is the number of grams of lead nitrate per 1 mole of lead nitrate. You can figure that out from the chemical equation and the atomic masses of the components. You multiply that by the conversion factor, and grams of lead nitrate in the numerator cancel with grams of lead nitrate in the denominator, and whatever answer you get when you multiply these things together, that will be the total number of moles of lead nitrate in that 0.2 gram sample. Okay? So now we know how many moles of lead nitrate need to be pulled out of the solution. The next thing that we have to ask ourselves is how many moles of the Ki are we going to need to combine with the lead nitrate in order to pull it all out? Well, the way we do that, take this number here that we started off with, number of moles of lead nitrate in our solution, and we're going to multiply that number by the relationship between moles of potassium iodide and moles of lead nitrate that we get from the balanced equation. What's that ratio? How many moles of Ki per mole of lead nitrate? From the balanced equation? 2. So there's 2 Ki's required for every 1 lead nitrate. So we can just put a 2 right there where I had the blank. 2 Ki's for every 1 lead nitrate. And then what that means is that all we really have to do is multiply by a factor of 2 whatever the number of moles of lead nitrate were that we had up there. And that new number is going to be the total number of moles of potassium iodide required.
If you were in the office, what do you
So
think
now
it
we
would
know
be?
the number of moles of potassium iodide that we
If you
need,
were in the office,
but
what
we
do you-
need to turn that into mass because you're going to have to go weigh out the appropriate mass of potassium iodide to add to your lead nitrate. So the next thing that we
Maybe
do
Jim.
is we convert moles of potassium iodide required to grams of potassium iodide required. We'll take that number there, the number of moles of Ki required, we'll stick it right here, and now we'll multiply it by the molar mass of the potassium iodide. We'll call this one Y. There's Y grams of potassium iodide for every 1 mole of potassium iodide. You can figure that out from your periodic table. Multiply those two numbers. Moles of potassium iodide cancel in the numerator and denominator. And we're left with a number that is the total number of grams of potassium iodide that we're going to need to remediate this. Okay? So you can go get that number of grams of potassium iodide, you'll add it to your solution. Now, there's one more calculation that we got to do, and that calculation predicts for us how much product we're going to form. Pretty easy calculation to think about in this reaction because we have exactly enough of each of the reactants to interact with each other. The calculation gets a little bit more complex when we have a particular reagent that is limiting. But in this case, we've got exactly enough lead nitrate to react with the amount of Ki that we have. And so we can use either one of these number of moles of reactants to figure out how much product gets formed. For this calc, I'm just going to take the number of moles of lead nitrate that we started with or that we've determined. I'm going to write that in right here. And then I'm going to look at the balanced equation and figure out the relationship between the number of moles of lead nitrate consumed and the number of moles of potassium iodide formed. What's this ratio? How many moles of lead iodide do we expect per a mole of lead nitrate? It's 1 to 1. So 1 mole of lead nitrate gives us 1 mole of potassium iodide. So we'll put this 1 right in here. Basically, just multiplying this original number of moles of lead nitrate by 1 gives us the predicted number of moles of potassium iodide, right? Now then you can take this number if you want and use the molar mass of potassium iodide to convert this to the number of grams of potassium iodide that you predict. Either way, what you've just determined, whether you calculated in moles or grams, is the predicted amount of product from this reaction. And we're going to use that in one more calculation, and that is the calculation of our yield. So at the end of the day, this reaction is going to look like this. You're going to take some lead nitrate, throw in some potassium iodide. You're going to be left with an aqueous solution that should be mostly potassium nitrate. You'll note that it's not entirely potassium nitrate. Not all of your lead iodide solid gets pulled out of this solution. You form this, you pour it on top of a funnel that's got a piece of filter paper in it. The soluble potassium nitrate drops through in the solution below, and the solid lead iodide stays stuck to your filter paper. You'll take that filter paper, you let it sit for a week so that it dries out. Right now it's full of lead iodide, but that lead iodide also has a lot of water in it. So we're going to let it dry out, and then we'll come back and we'll weigh it, and we'll take the ratio of the mass that we actually weigh to the mass that we predicted from the balanced equations, multiply that by 100, and that's our percent yield for the purification, remediation, whatever you want to call it. Does that make sense? Do we have any questions? Are we all on the same page? Do we get it? I feel like there's like 3 or 4 other things that I need to say, but I can't remember what they are right now, so I'm going to turn you loose, and then when I remember what it is I forgot to say, oh, here's what I forgot to say. Today's notes are graded, so we got those 3 sets of notes that I actually have to score. Today's notes are one of those, so be very careful about your note taking. Turn your notes in at the end of the day. The other thing is, we're working with aqueous solutions of lead and copper, which are contaminants because they're not healthy for us, yeah? And so wash your hands, try not to dip your fingers into these solutions too much any more than you have to. And if you do touch the solutions, try to get over to the sink and wash your hands up right away, okay? All right, let's get to work. Oh, yeah, you can start.